Usually when we try to measure how far apart two things are, it's pretty simple.
Right, just physical.
Exactly. It's tangible. You take a tape measure, you pull it from your couch all the way to your TV, and you just read the number on the little metal tape.
Yeah, it's the shortest physical path between point A and point B.
Right, a straight line. If the tape measure says 10 feet, it's 10 feet. Boom, done.
And our human brains, they evolved to understand that perfectly, that three-dimensional straight line distance is just baked into us.
But then you try to look under the hood of a modern artificial intelligence. You try to use that same logic.
And it falls apart entirely.
It really does. You try to measure the distance between the concept of, say, a king and a queen inside the mind of an AI, and suddenly that physical tape measure it's completely useless.
Because you're no longer measuring physical space. You're trying to measure the distance between ideas.
Right. And that is exactly what we're exploring today. Welcome to this deep dive.
It's going to be a heavy one.
It is. But before we get started, I actually have a very specific and frankly, somewhat intimidating mission today.
Oh, lay it on me.
I have been instructed to give a massive, enthusiastic shout out to you, the listener, but specifically to a very particular group out there calling themselves the Bussin Sigma Scholars of Edward Little High.
Wow. Okay, that is quite the title.
Right. I am not entirely sure what level of academic rigor qualifies someone as a Bussin Sigma scholar.
I'm assuming it's very rigorous.
Oh, it has to be, because I am told that you scholars have been grappling with some intensely heavy mathematics lately.
Well, they came to the right place.
Exactly. So today we are going on a journey just for you, the Bussin Sigma scholars, and of course for anyone else who just wants to understand the hidden architecture of artificial intelligence.
And we are looking at a truly fascinating stack of sources today to do this.
Yeah, tell us what we're working with.
Well, we're pulling from Terence Tao's mathematical notes on measure concentration, which is dense stuff.
Very dense.
We've also got some deep theoretical papers on manifold geometry, foundational texts on measure theory, and time delay embeddings.
And we're even crossing over into practical engineering, right?
Exactly, looking at practical guides from vector databases like Milvus.
It's a ton of ground to cover. But our mission today is to uncover the deep, hidden connection between some incredibly abstract math, specifically things called Borel sigma algebras and input reducers.
Which sound terrifying, but we will break them down.
We will, and we're going to connect those to why AI latent spaces absolutely rely on angles, meaning cosine distance, rather than that straight line Euclidean tape measure, to actually understand what words or images mean.
It really is a profound transition. I mean, we are moving from the physical intuition of space into a purely informational topology.
Informational topology, I like that.
Yeah, we essentially have to completely rewire how we think about geometry.
Okay, let's unpack this. So imagine you're trying to map the entire human experience into a massive multi-dimensional spreadsheet.
Every thought, every image, every word.
Right. How do you guarantee that closeness in that spreadsheet actually translates to closeness in real life? If the word dog and the word canine are near each other in the math, how does the system actually know they mean the same thing?
That is the core problem we are solving today.
And to do that, we have to start at the very foundation of reality. Or, well, mathematical reality anyway.
Right, because before we can even talk about an AI understanding data, we have to establish where that data lives before it gets fed into the machine.
Like its natural habitat.
Exactly. Text, images, sensory data, in its raw, uncompressed form, it exists in what mathematicians call a topological space.
Okay.
And specifically for modern machine learning, we often mathematically model this as a Polish space.
Okay, time out. I'm stopping you right there. A Polish space. Just to clarify for anyone listening and for the scholars at Edward Little High, this has nothing to do with the actual country of Poland, right?
No, not the country itself, though it is named in honor of a group of brilliant Polish mathematicians.
Ah.
People like Stefan Banach and Łako Sierpiński, who essentially pioneered modern point-set topology back in the 1920s and 30s.
Got it. Okay, so what actually is it? If my raw data, my messy pile of text and images, is a Polish space, what does that mean in plain English?
Well, a Polish space is formally defined as a separable, complete metric space.
You and I have very different definitions of plain English.
Fair enough, fair enough. Let's break those two words down. Separable and complete.
Please do.
Imagine you are trying to map out a vast ocean. If the space is separable, it means that even though the ocean has infinitely many points of water,
Just a continuous, endless sea.
right, even so, you can drop a countable number of buoys into it, say 1 buoy every square mile.
Okay, I'm picturing the buoys.
And no matter where you swim in that infinite ocean, you will always be reasonably close to a buoy.
Oh, I see.
In math, we call that having a countable dense subset. It basically means the space is vast, but it's manageable. It can be approximated.
Okay, I really like the buoy analogy. So the data universe is infinite, but we can drop enough reference points to keep track of it all.
Exactly.
So what about complete? What makes the space complete?
Complete means there are no microscopic black holes in your ocean.
Black holes.
Yeah, so if you follow a sequence of points that are getting closer and closer together, they will eventually hit a real, solid destination that actually exists within that space,
As opposed to what?
as opposed to just falling off the edge of reality into a missing point. There are no gaps.
So it's a safe, well-behaved universe, no missing pixels, no data that just vanishes into a math error.
Precisely. It gives us a rigorously well-behaved environment.
Yeah.
And the reason this matters for AI,
Yeah, why do we care?
because when we derive a mathematical structure called a Borel space from a Polish space, we get what's called a standard Borel space.
Right.
And the beautiful, almost magical thing about uncountable standard Borel spaces
Right.
is that they're all isomorphic.
Isomorphic, meaning they have the same shape.
They share the exact same underlying mathematical skeleton.
Wait, hold on. Does that mean what I think it means?
What are you thinking?
If I have a raw data set of, say, 5 million cat pictures,
Okay.
and a completely different raw data set of 5 million paragraphs of text that describe cats,
Right.
are you saying that because they are both modeled in these standard Borel spaces, their foundational math is identical?
That is exactly what I'm saying. Whether it's an audio wave, a pixel grid, or a string of text, on a foundational topological level, they are isomorphic.
That is mind-blowing.
It's the bedrock of modern AI. It's what allows disparate data types, multimodal data, to eventually be mapped into the exact same AI latent space while maintaining comparable semantic structures.
It's like finding out that the blueprint for a skyscraper and the blueprint for a submarine are written in the exact same universal language.
It really is. But here's the catch.
There's always a catch.
To actually build anything with that universal blueprint, we need a rigorous way to define the subcomponents of that space. And crucially, we need to be able to measure them.
Measure them, right.
Which brings us to the core of the Bus and Sigma Scholars curriculum today. The Borel Sigma algebra.
Ah, yes. The Borel Sigma algebra. I've been waiting for this. So let's break this down very carefully. What exactly is it, and why can't we just measure things without it?
Well, to understand why we need it, you have to understand a rather terrifying piece of mathematics called the Banach-Tarski paradox.
A paradox. Okay, I'm intrigued.
So back in the early 1900s, mathematicians realized that if you don't establish strict rules for how you group points together into space, infinity completely breaks reality.
Breaks reality how?
The Banach-Tarski paradox proved mathematically that if you take a solid 3D sphere, let's say a single green pea,
A P. Got it.
and you slice it up into 5 highly specific, infinitely jagged, fractal-like pieces,
Okay, weird slicing, but sure.
you can then take those exact same 5 pieces, shift them around, and reassemble them to create 2 solid spheres, both the exact same size as the original pea.
Wait, what? No, that makes no sense. You can chop up a P and reassemble it into 2 P.
Mathematically, yes.
Or, like, could you chop it up and reassemble it into something the size of the sun?
Yes. If you allow what we call non-measurable sets, these chaotic, infinitely jagged collections of points, the entire concept of volume, of distance, of measure, completely ceases to exist.
So basically 1 equals 2.
Exactly. The math just shatters.
Okay, so if we feed a non-measurable set into an AI, the AI's brain essentially melts because it can't determine the probability or the weight or the size of anything.
Right. The AI would encounter a ghost in the data. So we need a filing system, a strict, unbreakable set of rules that dictates exactly what groupings of data are actually allowed to exist and be measured.
And that rulebook is the Borel Sigma algebra.
That's it. It is formally defined as the smallest collection of subsets containing all the open sets of that space.
Open sets.
Yes, and this collection must be closed under 3 specific operations: countable union, countable intersection, and complementation.
Okay, I'm definitely going to need an analogy here because that is a very dense mathematical sentence.
Let's do it.
Let's translate that into the real world. Let's imagine our raw data space is a gigantic, chaotic grocery store. The physical building itself is our Polish space.
I like that. The physical store is the space. Now, the Borel Sigma algebra is generated by open sets. So in your grocery store, an open set is a basic, undeniable physical grouping.
Like a physical shelf of cereal or a bin of apples.
Exactly. Generation by open sets is crucial because it ensures that neighborhood relationships, closeness, are actually measurable.
So if two boxes of cereal are physically near each other on the shelf, the algebra can mathematically capture that proximity. It essentially locks the aisles into reality.
Yes, it grounds the math.
Yeah.
But a store isn't just isolated shelves, right? We need to be able to group things together logically.
Right.
This is where those three rules come in. First, closure under countable union.
Meaning I can say aisle 4 and aisle 5 are now a single measurable category called breakfast and baking.
Precisely. You can combine groupings as long as you can count them, and the math won't break.
Okay, that makes sense. What's the second rule?
Closure under countable intersection. This means you can apply multiple constraints overlapping each other.
So I can say, I want the exact intersection of the snack aisle and the gluten-free section.
Yes. It allows for the infinite, rigorous refinement of features. You can keep narrowing down the criteria snack, gluten-free, under $5, and the resulting set is guaranteed to still be mathematically measurable.
I see. And finally, the third rule, closure under complementation, which honestly seems super important for AI.
It is arguably the most important for training.
Because this means if I have a perfectly defined, measurable category for dairy, my system now perfectly understands and can measure the exact opposite. Everything in the store that is not dairy.
Which is absolutely vital. It allows for the rigorous definition of negative samples and class boundaries during machine learning training.
Because without complementation, an AI might learn what a cat is, but it couldn't mathematically comprehend the concept of not a cat.
Exactly. Defining a Borel measure on this algebra guarantees that any probability distribution on the inputs can be strictly analyzed. We aren't just guessing anymore.
We have absolute mathematical certainty that we can measure the probability of any event, any grouping of data occurring in this space.
The Borel sigma algebra is the ultimate paradox-proof rulebook. It tames that infinite ocean of data so we can actually measure it.
Okay, but here's the thing. An AI doesn't work in the raw, real world, right? It doesn't process the entire physical grocery store.
No, it would be too computationally heavy.
It works in a latent space, a compressed, dense vector space of numbers. So somehow we have to move all the data from the physical grocery store into a highly compressed mathematical spreadsheet.
And this transition is what mathematicians call a push-forward map.
Push-forward map.
We use what is known as a reducer, a mapping function, to reduce that massive input space into a dense vector space, which we usually denote as math today.
Right.
But for this to be mathematically valid, the mapping must be Borel measurable.
I'm going to be honest, you just said we are pushing a measure forward, and my brain completely stalled out for a second.
It's a weird concept to visualize.
How do you push a probability measure? What does that even look like?
Well, when we map the data from the input space to the latent space, we aren't just taking individual disconnected data points and teleporting them one by one.
Okay.
We are actually taking the entire Borel measure, the complete probability distribution of the data, the mass, the shape, the neighborhoods, and transferring that entire structure into the latent space.
So if I'm picturing a sandcastle on a beach, where the sandcastle represents my probability distribution,
Nice analogy.
pushing the measure forward is basically like using a shovel to move the entire sandcastle into a small wooden box, but trying to preserve the exact volume and the relative positions of all the little towers.
That is an excellent way to visualize it. Mathematically, the pre-image of every Borel set in the target latent space must map back to a valid Borel set in the original domain.
Meaning the mathematical structure cannot be broken during the move.
Exactly.
Yeah.
But, as you can probably imagine, how you shovel that sand completely changes the final shape it takes inside the box.
Oh, absolutely. And this is where we really have to dive into the core of our outline today for the scholars.
The reducers.
Yes, there are different ways to shovel the sand. We are going to intricately detail 3 distinct examples of these reducers over the input space.
Because how we reduce the data creates a specific geometry in that box.
Right, and that geometry starts to hint at why we eventually need angles cosine similarity to understand semantics. So let's start with reducer example 1, an old classic in data science. Principal component analysis, or PCA.
Right, PCA is a linear reducer. Its fundamental mechanism works by mapping data onto the eigenvectors of the covariance matrix that have the largest eigenvalues.
Okay, time out. Eigenvectors of the covariance matrix sounds incredibly intimidating to anyone who hasn't taken advanced linear algebra recently.
Fair. It is a mouthful.
If I'm picturing my raw data as a giant 3-dimensional cloud of floating dots like a massive swarm of bees, what is an eigenvector actually doing to them?
Let's use that swarm of bees. Imagine the swarm isn't perfectly round. Let's say it's shaped somewhat like an American football, kind of stretched out in one specific direction.
Okay, I see the football shape.
The covariance matrix is essentially just a mathematical description of how those bees are spread out. And the eigenvectors are the invisible structural bones of that swarm.
The bones.
Yeah. The first eigenvector is simply an arrow pointing straight through the longest part of the football. It is the single direction where the data is stretched out the most.
Okay, I see it. It's the longest axis of the swarm.
Right. And the eigenvalue is just a number telling you how long that stretch actually is.
Right.
So PCA works by finding that longest arrow and saying, hey, this is the most important feature of the data.
Is it has the most spread.
Exactly. It squashes the 3D swarm down onto a 2D piece of paper, perfectly aligning the paper with that longest arrow to capture the maximum amount of physical spread.
So PCA is entirely obsessed with absolute magnitude. The widest physical spread is all it cares about.
Correct. The Borel impact here is that PCA creates a push-forward measure that is entirely focused on absolute variance in straight-line Euclidean terms.
It preserves the Borel sets by just squashing them along the axes of maximum physical distance.
Exactly.
But there's a massive catch there when it comes to semantics, isn't there?
Oh, a huge one.
Let's say I'm analyzing language. I have the word the, which appears, I don't know, 10 million times in my data set.
Right.
Its variance, its absolute magnitude is going to be massive. It's a huge stretch in the data. But then I have the word spectacular, which appears maybe 10 times.
And what does PCA do?
PCA is going to look at the raw magnitude of the word the and think it is the single most important feature in the universe, just because its volume is huge.
Exactly. It gets completely distracted by the noise of frequency. But semantic meaning isn't about how loud a word is or how frequently it appears.
It's about context.
Yes, it's about the ratio of its features, what other words it naturally hangs out with.
Right. The words spectacular and amazing might have tiny magnitudes, but they share the exact same contextual ratios.
And PCA's Euclidean focus fails completely here. It distorts the push-forward Borel measure by over-prioritizing scale. It basically treats the loudest person in the room as the most meaningful.
Which introduces our very first intuitive need for angular alignment. Cosine similarity, which we will discuss later, looks at the angle of those eigenvectors rather than how far they stretch.
Right, it looks at the direction, not the length.
But before we get to cosine, let's look at reducer example 2. Because if PCA is too linear, what if we use a non-linear method, like TSNE or UMP?
Yeah, if PCA is just drawing straight lines to the data, TSNEA handles the grocery store very differently.
How so?
These nonlinear reducers operate on a completely different philosophy. Instead of looking for global variance, the longest line through the whole swarm, their mechanism focuses heavily on preserving local neighborhood structures.
Neighbor.
Right. They want to ensure that if two data points were very close together in the massive, high-dimensional input space, they remain very close together in the compressed latent space.
And this ties directly back to our Borel sigma algebra, because as we established earlier, Borel algebras are generated by open sets, which mathematically represent those physical neighborhoods on a shelf.
Yes. TSNE explicitly attempts to preserve the topological relationships of the original Borel sets.
How does it do it mathematically?
Well, it calculates a probability distribution of who is neighbors with who in the high-dimensional space, and then creates a new probability distribution in the low-dimensional space and tries to make them match.
And it matches them by minimizing something called the Kullback-Leibler divergence, right? The KL divergence. Can we unpack that for a second?
Of course. KL divergence is essentially a way of measuring the asymmetry between two probability distributions.
Give me a real-world example.
Imagine you have a recipe for a cake, and your friend has a slightly different recipe for a cake. The KL divergence essentially measures how surprised you would be if you tried to bake your friend's cake using your own assumptions about the ingredients.
Okay, that makes sense. So TSNE minimizes this surprise.
Exactly. It adjusts the positions of the points in the latent space until the local neighborhood probabilities look as incredibly close to the original input space as possible.
But to pull that off, to force those probabilities to match, it has to severely warp the space, doesn't it? Because you are trying to force high-dimensional relationships into a smaller, flatter box.
It absolutely warps it.
It's like taking our massive physical grocery store map and crumpling it up into a tight ball of paper so that the apples and the oranges are still physically touching each other, even though they used to be 5 aisles apart.
That is a brilliant visualization. And this is exactly where Euclidean distance fails us yet again.
Because of the crumpled paper?
Right, because the push-forward measure has been bent, twisted, and crumpled to keep these local neighborhoods intact. The resulting manifold is incredibly complex.
Yeah, if you try to measure the distance between two things in that crumpled ball using a straight Euclidean tape measure, you might measure a straight line directly through the empty air between the folds of the paper.
Exactly. You are completely ignoring the actual topological surface of the store.
You're measuring the shortcut through the air, not the path on the paper.
Precisely. Measuring a straight Euclidean line across this new, complex manifold is practically useless. It tells you nothing about the true semantic distance.
So what determines the semantic proximity then?
The true semantic proximity is determined by how these preserved neighborhoods align with each other. The orientation, the angle of the local structure, becomes the meaningful signal. The topology practically demands an angular metric.
Okay, that's reducer 2. Now let's get into the heavy hitter, reducer 3.
This is where it gets really intense.
It does. Reducer 3 is measure-theoretic time delay embedding, specifically using clustering and partitioning. This comes directly from the provided research on learning full-state reconstruction maps.
It is dense, but it is so fascinating.
It truly is. So in PCA and TSNE, we were mostly talking about static data, images, text. But in this third approach, we are looking at dynamical systems.
Systems that change over time, like weather, fluid dynamics, or moving machinery.
Right. And the mechanism here relies on something called Taken's embedding theorem, which to me sounds like literal magic. Let's translate this for the listener.
Let's do it.
Imagine you are tracking a massive, complex hurricane. It has air pressure, wind speed, humidity, temperature, thousands of variables all interacting and happening at once.
But you don't have a weather satellite.
Exactly. You only have a single basic thermometer tied to a pole outside your window.
A single one-dimensional partial observation of a massive chaotic system.
Right. And Taken's theorem mathematically proves that if you track that single thermometer long enough and look at the time delays, like the temperature right now, the temperature an hour ago, 2 hours ago, 3 hours ago,
Yes.
you can actually use that sequence of single numbers to perfectly reconstruct the hidden multidimensional geometry of the entire hurricane.
It feels absolutely impossible, but the topology guarantees it. The history of the single variable encodes the state of all the other variables that interacted with it.
That is wild. But how do we actually create a reducer out of this? You mentioned it depends on measure theory.
It does. We take that long time series of temperature observations and we partition those trajectories into discrete, what we call Voronoi cells, using an algorithm like Kameen's clustering.
Let's stop at Voronoi cells. What are those?
Imagine a map of cell phone towers spread out over a city. A Voronoi cell is simply drawing borders around the towers so that any point inside a specific border is mathematically closest to that specific tower.
So we are dividing the continuous time series into discrete regional chunks.
Got it in one. The Borel impact here is profound. Each of those Voronoi cells, each cluster of time-delayed observations, now represents a discrete empirical probability measure.
Well, we are looking at how much time the hurricane spends in state A versus state B.
Yes, and the reducer maps these probability spaces from the input manifold to the latent space by matching the moments of the measures.
The moments, meaning their center of mass, their spread.
Exactly.
Wait, hold on. It doesn't just match the raw numbers, the point-wise mean squared error.
No, and this is the crucial insight. Point-wise mean squared error is essentially just Euclidean distance.
Right.
If we use that, the system would aggressively overfit to the noise. Think about your thermometer outside the window. What if a bird lands on it?
Or what if the sun hits it directly for 10 minutes?
It creates a huge spike in the temperature reading, a massive absolute magnitude that has nothing to do with the hurricane.
Right, it's just a glitch.
Exactly. If my thermometer gave me noisy high magnitude readings, a Euclidean measurement would try to match that noise perfectly.
It would think the bird landing on the thermometer was a critical structural feature of the hurricane.
Yes, and it would completely fail to reconstruct the true state.
But by pushing forward discrete probability measures, we avoid that trap entirely.
The paper notes, we map these probability distributions directly. We move the entire distribution. Matching the shapes of these distributions natively relies on orientation and alignment rather than absolute distance.
Because the absolute magnitude of these localized measures in the delay space is heavily influenced by how densely you sampled the data or how much extrinsic noise like the bird was present.
Exactly. The semantic similarity of the embeddings in the latent space is natively protected by treating the data as distributions where alignment, or cosine similarity, is the robust metric.
Absolute Euclidean magnitude is just an artifact of the thermometer glitching.
Exactly.
Okay, so we've reduced our data, we've pushed our meticulously defined Borel measure forward using PCA or TSNE or time delay clustering. The sandcastle is finally in the box.
We are now sitting inside the latent space of the AI.
And here's where it gets really interesting, folks, because this latent space isn't just 3D. It's hundreds or even tens of thousands of dimensions.
And when you enter high dimensions, human intuition about distance doesn't just bend, it absolutely shatters.
We encounter what is famously known in machine learning as the curse of dimensionality and a deeply unintuitive mathematical phenomenon called the concentration of measure.
We really need to spend some serious time here.
We do because reading Terence Tao's notes on measure concentration melted my brain a little bit. I want you to talk to me about Paul Levy's inequality and spherical concentration. I want you to walk me through exactly what happens to geometry when we add 1,000 dimensions.
I will do my best because it is deeply, deeply counterintuitive.
Take it slow.
Let's start with something familiar, a simple sphere, a 3D globe, the Earth. Let's mathematically denote this sphere as said Tutter, where no dollars is the number of dimensions. So Earth is 3 dollars there's height.
Okay, I have a globe in my head. I'm with you.
Now, let's apply a normalized surface area measure to it. Let's take a set of points on the globe, which we will call set dollars, and we will paint them red.
Okay.
Let's say the area set dollars is exactly half of the sphere. The entire northern hemisphere is painted red.
Easy enough. The equator perfectly divides the red top from the unpainted bottom.
Perfect. Now, in 3D space, if I ask you to find all the points that are, say, 1 inch away from the red hemisphere, you just draw a little 1-inch band right below the equator.
Right. And the volume of that band is pretty small compared to the whole Earth. Most of the southern hemisphere is still very far away from the red part.
Exactly. Now, we start adding dimensions.
Yeah.
We stretch the globe into a hypersphere.
Right. Paul Levy's inequality proves a terrifying mathematical bound about this hypersphere. It proves that the area of the set of points that are farther than some small distance epsilon away from that red hemisphere decays exponentially as the dimensions increase.
Exponential. Yes. The specific mathematical bound is that the remaining area is less than or equal to 2r1 epsilon 22.
Whoa. Okay, let me translate that equation for anyone driving right now because that is heavy.
Please do.
What that math means is that as not a dollar, the number of dimensions gets huge.
Yeah.
The negative exponent just explodes. The remaining area shrinks to zero exponentially fast.
Yes.
Meaning almost the entire volume of the high-dimensional sphere gets sucked into a microscopic razor-thin strip right along the equator.
It does.
The poles, the deep north and deep south of the globe, basically cease to exist in terms of volume.
Exactly. Imagine your globe again. In 1,000 dimensions, 99.999% of the mass of the entire globe is located within a millimeter of the equator.
That is insane to picture.
It is, and the disintegration of Euclidean distance happens right here.
Why does the tape measure disintegrate?
Because if almost all the volume of the sphere is concentrated right at the equator, and you pick any 2 random points on this high-dimensional sphere,
Right.
they're both going to be on the equator.
Right, because that's where all the space is.
And because of the geometry of how high dimensions fold out, their straight-line Euclidean distance will almost always be incredibly close to the square root of 2.
Square root of 2. Every single time.
Almost every single time.
I remember reading that and just staring at the page. If you pick any 2 random points in a 1,000-dimensional space, they are always the exact same distance apart.
It's called distance concentration.
Imagine being in a room where no matter who you pick, your best friend, your worst enemy, a total stranger, they are always exactly 1.41 feet away from you.
You wouldn't be able to tell who is close to you and who isn't.
Right, because everyone is identically spaced out.
This distance concentration effect mathematically ruins our latent space. And to understand why it ruins it, we have to remember how Euclidean distance, the Tolle-Toulet-True norm, is actually calculated.
It's basically the Pythagorean theorem, right? Tell of x plus b2 equals c2, but scaled up for lots of dimensions.
Exactly. It incorporates every single dimension into a massive sum of squares. It looks at the difference between point A and point B on dimension 1, squares it, looks at dimension 2, squares it.
All the way up to dimension 1,000.
And then it takes the square root of that giant sum.
And here's the fatal flaw. If most of those 1,000 dimensions are just irrelevant variance or artifact noise from our reducers pushing the measure forward,
then that noise accumulates. Because you are summing every single dimension, the sheer volume of tiny random differences across, say, 950 noisy dimensions completely overwhelms the actual meaningful signal hidden in the 50 dimensions that actually matter.
The noise dominates the metric. As a result, the tape measure fails completely because it is measuring 95% noise and 5% signal.
It's a total failure of the metric.
It's like trying to judge how close two friends are by listing every single measurable trait about them.
Let's say you want to know if Alice and Bob are close friends.
Okay, Alice and Bob.
You list their favorite movie, which is a massive signal, right? That tells you a lot. But then you also list the color of their socks today,
Irrelevant.
what they had for breakfast on a Tuesday in 2015, the exact number of hairs on their head, the exact number of cells in their bodies.
Oh, I see where you're going. If you weigh every single trait equally, which is literally what Euclidean distance does by summing them all up, the sheer volume of random, noisy differences in their cellular count completely drowns out the fact that they share deep core values and love the same hobbies.
The noise makes them look like strangers.
Exactly. You desperately need a way to filter out the magnitude of the noise.
Which brings us to the angular savior. If Euclidean distance fails us because it greedily accumulates magnitude noise across every dimension, we must turn to a metric that ignores magnitude entirely.
We must turn to cosine similarity.
Yes, we finally arrive at cosine similarity.
Okay, let's define this for the scholars. We talk about angles, but what is the actual math happening here?
Cosine similarity is the dot product of two vectors divided by the product of their magnitudes.
So the formula is text cos theta equals the dot product of vector A and vector B divided by the length of A times the length of B.
That's the one.
What is this division actually doing mathematically to the data?
Think about a vector as an arrow pointing out from the center of a graph. It has a direction, and it has a length, its magnitude.
Right.
By calculating the dot product, you find how much those two arrows overlap. But then, by dividing that dot product by the lengths of the two vectors, you are mathematically normalizing them.
Normalizing them, meaning what?
You are effectively stretching or shrinking every single vector in the entire space so that they all have an exact length of 1.
So you are projecting every vector onto the surface of a unit hypersphere. It entirely strips away the length of the vector.
Exactly. The AI goes completely blind to the magnitude. It only looks the angle, the theta between them.
Okay, so going back to our reducers and our Borel algebra.
Let's tie it all together.
We took our perfectly measurable grocery store and we pushed the Borel measure forward using PCA, TSNE, or clustering.
We shoveled the sandcastle.
But because we pushed it into this bizarre 1,000-dimensional space where volume concentrates at the equator and Euclidean distance breaks down due to noise accumulation, projecting out the radial component saves the semantics.
It does. Let me phrase it in rigorous measure theoretic terms. By using cosine similarity, we are essentially swapping our measuring stick.
Okay.
We are abandoning the Lebesgue measure on MathBRE, which measures absolute 3D volume and suffers from the curse of dimensionality for the hair measure.
The hair measure.
Yes, the hair measure on the sphere. While the Lebesgue measure looks at the entire bulk volume of the space, the hair measure is a rotationally invariant way of measuring the area strictly on the surface of the sphere.
Fair. So by sticking strictly to the surface, we preserve the angular alignment, which we can think of as the phase information or the contextual feature ratios that were mapped from the original Borel neighborhoods in the input space.
Yes, and we completely discard the radial magnitude, the length, which, as we saw with the time delay embedding thermometer glitch and PCA's obsession with frequency, is often just an artifact of input scalar noise.
It is an incredibly elegant geometric rescue. This makes absolute sense when you look at natural language processing in practice.
It really does.
Let's go back to our word example. Let's say you have a massive word embedding model. The word "the" is incredibly frequent.
Right.
Because the model sees it constantly, its vector magnitude, its length is going to be massive. It's a huge arrow. But a rare word that means exactly the same thing in a specific context might have a tiny vector.
Exactly. And if you use Euclidean distance, the math looks at the tips of those arrows and says, well, one is 10 miles long, the other is 10 inches long. The distance between their tips is huge. These words are totally different.
It fails. But cosine distance looks at the direction they are pointing, completely ignores the 10 miles versus 10 inches, sees they are perfectly parallel, and says, hey, these mean the same thing.
It focuses on the pattern of the features, not the intensity of the features.
Exactly. And there is a fascinating mechanical practical detail here, highlighted directly in the engineering documentation from the Milvis vector database, which is one of our key sources today.
Oh, I love this part.
Ah.
Because it bridges the gap between high-level topology and actual software engineering.
It really does. It turns out if you normalize your embeddings beforehand, if you mathematically force them all to have a length of 1 before you even store them in the database, the Euclidean distance actually becomes a strict mathematical function of the cosine similarity.
Yes, the formula resolves beautifully. The squared Euclidean distance between two normalized vectors is exactly equal to 201 by the set.
Meaning, as the cosine similarity goes up, the Euclidean distance goes down in absolute lockstep. The ranking of search results will be 100% identical.
Identical.
If a vector is your number one closest match using cosine, it will also mathematically be your number one closest match using Euclidean distance on a normalized data set.
Which raises an immediate, highly practical question for anyone building an AI app.
Right, if they rank exactly the same when normalized, why does the entire industry standardize on choosing cosine similarity? Why not just use Euclidean?
If the math converges, why the preference? It comes down to practical engineering, computational interpretation, and pure speed.
Tell me about interpretation first.
Cosine similarity provides predictable, strictly bounded thresholds. The score is always mathematically bound between non equals 1 and 1.
Okay, yeah, that's clean.
It makes it highly intuitive for a developer or a researcher. A score of 0.99 means the vectors are highly similar. A score of 0 means they are orthogonal, totally unrelated.
Whereas a Euclidean distance ranges from 0 to 2 on normalized data, which is just weird to debug. Oh, yes, my vectors have a distance of 0.02. They must be close. It's just less intuitive for a human to read.
Furthermore, and this is the real bottleneck for global scale AI, cosine similarity on normalized vectors simplifies entirely to just calculating the dot product.
Just simple multiplication and addition.
Exactly. Computing a dot product is computationally far faster for a CPU or GPU than calculating a Euclidean distance, which requires squaring differences, summing them up, and then taking a computationally expensive square root.
Right. When you are using approximate nearest neighbor libraries like Fay to search through hundreds of millions of AI embeddings in milliseconds, that marginal overhead of the Euclidean square root calculation becomes a massive system bottleneck.
Cosine is mathematically elegant, it's topology appropriate, and it's computationally blazing fast.
It's basically the holy grail of metric geometry. It perfectly rescues us from the curse of high-dimensional spherical concentration. It respects the Borel neighborhoods we carefully pushed forward with our reducers, and it runs fast enough on a server to power global AI search engines. It's perfect. Ah.
There's always a but in the deep dive.
There's always a but in mathematics.
There.
We have spent the last half hour building up cosine similarity as the angular savior of AI semantics.
We have.
But we have to look critically at the paper semantics at an angle, when cosine similarity works until it doesn't. Catchy title.
It turns out, treating vector magnitude purely as trash, as artifact noise, creates its own massive blind spots.
Right, because I actually had a friend who builds multimodal models tell me once that he hates normalizing his vectors because he loses data.
He's right. The core assumption of cosine similarity is that direction is everything and length is nothing. But modern research shows that vector norms, the lengths, often encode absolutely critical metadata about the embedding itself.
Like what kind of metadata?
Let's look at multimodal models like CLIP, which are trained to align text with images. In these spaces, the norm of the vector often encodes the model's certainty or the alignment strength.
So a much longer vector might indicate that the model is highly confident in its representation of that specific image.
Exactly. And in word embeddings, the norm can encode the informativeness of a word. A very specific, highly informative word has a longer vector than a generic filler word.
But by mathematically forcing everything onto the unit sphere, cosine similarity violently erases these vital signals.
It wipes them out completely. A highly confident, deeply informative embedding is treated exactly the same as a weak, uncertain, noisy embedding, simply because they happen to point in roughly the same direction.
It's like having two people point out a suspect in a police lineup.
Okay, let's hear it.
One is an eyewitness who saw the whole crime up close in broad daylight and is pointing with absolute rigid certainty. The other is a guy who just walked in off the street, is completely blindfolded, and just happens to be pointing his finger in the exact same direction by total coincidence.
That's a perfect analogy.
Cosine similarity looks at that lineup and says, their fingers are perfectly parallel, therefore their testimonies are equally valuable.
It completely ignores the weight behind the direction. And this erasure of magnitude leads to severe structural issues in the latent space. primarily two phenomena known as anisotropy and frequency bias.
Let's unpack anisotropy first, because earlier we were picturing our data nicely spread out all over the surface of this massive high-dimensional sphere. But that's not actually what happens in practice, is it?
No, not at all. In real-world, deeply layered neural networks, embeddings are almost never uniformly distributed across the sphere. They suffer from anisotropy, meaning they often occupy a very narrow, tightly packed cone in a single corner of the latent space.
Imagine throwing a massive party in a huge mansion, and instead of people mingling in all the rooms, 90% of the guests just cram themselves into one tiny corner of the living room.
Exactly. This creates a severe hubness problem. Because everything is squished into this high-density hub, cosine similarity struggles immensely to distinguish semantic content.
Right, if you try to figure out who is talking to who just by the angle they're standing at, it's impossible because everyone is practically on top of each other. The angles between totally unrelated concepts become vanishingly small.
Everything looks highly similar to everything else,
And then there's frequency bias.
which is particularly insidious in large language models. High-frequency tokens, very common words or subwords, can artificially inflate the cosine similarity between two completely unrelated sentences, simply because those common words dominate the angular direction of the sentence embedding.
So the geometry basically gets hijacked by the most common terms.
Yes.
So, wait, let me get this straight. Euclidean distance fails because it measures the magnitude noise. Cosine similarity fails because it deletes the magnitude confidence. We are stuck between a rock and a hard place here. How is modern data science actually fixing this? What is the middle ground?
There are a few very promising approaches actively being researched to fix this. One is using norm-aware measures like the word rotator's distance, or WRD, or a metric simply called scaled sim.
How do those work?
They explicitly factor the difference in vector magnitudes back into the equation right alongside the angular difference. They create a mathematically weighted balance between orientation and length.
So it's like putting the tape measure and the protractor together.
Yeah, exactly. You get the robust structural alignment of the angle, but you retain a penalty if the confidence levels, the lengths, are drastically different.
That's smart. What's the other approach?
Another approach is post hoc isotropization.
Isotropization, making the space isotropic uniform in all directions.
Yes. This involves taking the embeddings after they're generated by the model and applying mathematical techniques like mean centering or whitening the covariance matrix.
Essentially, you take that crowded corner of the party and you mathematically force the vectors to spread out and use the entire surface of the sphere evenly.
Exactly. You destroy that narrow cone of anisotropy before you apply the cosine calculation.
That makes total sense. So to bring this all together for our Bus and Sigma scholars, let's trace the full journey of our data today.
It's been a long journey.
It has. We take our messy infinite input space, the raw universe. We define it with a rigorous Borel sigma algebra, preventing mathematical paradoxes, and guaranteeing we can actually measure the probability of our concepts.
We lock the aisles in the grocery store.
Right. Then we push that measure forward through reducers like PCA looking for variance, TSNE looking for KL divergence in neighborhoods, or time delay clustering looking at the moments of Voronoi cells. We compress the data into a latent space.
We move the sandcastle into the box.
But because that box is thousands of dimensions, Euclidean distance breaks down entirely due to spherical measure concentration. Every point pushes to the equator, noise accumulates, and all points appear to be the exact same distance apart.
The tape measure fails.
Cosine similarity rescues us by swapping the Lebesgue volume measure for the hair surface measure. It ignores magnitude and looks only at the angle, perfectly preserving the semantic ratios.
But UT, while it saves us from the curse of dimensionality, treating magnitude purely as trash creates its own blind spots, erasing the model's confidence and creating frequency bias and anisotropy.
Cosine similarity works perfectly until it doesn't.
That is a phenomenal synthesis of the entire geometry.
Thank you.
However, there is one final, incredibly provocative concept hidden in the margins of our source material today. A concept that basically flips this entire hour-long discussion on its head.
Oh, I love this. Lay it on me. A good plot twist at the end.
We just spent all this time debating how to measure the distance between 2 points in a latent space. Euclidean tape measure versus cosine protractor.
Right.
But if pushing forward Borel measures into latent space creates all these metric headaches, anisotropy, frequency bias, noise accumulation, what if we stop trying to measure the distance between static points entirely?
Wait. If we don't measure the distance between points, what are we measuring?
The source material briefly mentions a field called optimal transport, specifically something called the Wasserstein distance.
Optimal transport, like
Yeah.
logistics, moving boxes around.
Exactly like logistics. In optimal transport, you don't treat data as a single point vector. You treat it as a probability distribution, a pile of Earth, a landscape of mass. Instead of asking for the angle between 2 points, the Wasserstein distance measures the exact cost of moving one probability distribution until it perfectly overlaps with another.
Whoa!
It completely bypasses the Euclidean versus cosine debate. You calculate the minimum energy required to reshape the entire Borel measure of concept A into the complete Borel measure of concept B.
So instead of asking how far apart are the peaks of these two sandcastles, or are the flags on these two sandcastles pointing in the exact same direction,
Right.
you ask a fundamentally different question. How many grains of sand do I have to mathematically shovel, and how far do I have to carry them to manually terraform sandcastle A into sandcastle B?
Precisely. It is the ultimate, pure, measure-theoretic approach to semantics. It doesn't compress the distribution into a vector that loses its confidence or its shape. It respects the entire mass of the data.
That is deeply mind-bending, treating data not as rigid arrows, but as dynamic, shifting landscapes of mass. I think my brain has officially hit its processing limit for the day.
It is a lot to take in, but that is the frontier of geometric deep learning.
Well, to the Bussin Sigma scholars of Edward Little High, and to everyone else who hung on through this deep dive, we hope you survived this intense mathematical journey.
You've earned a break.
We went from the physical tape measure in your living room to the paradox-proof topology of Borel algebras, into the high-dimensional hyperspheres of AI, and finally to shoveling sand in optimal transport. Take a walk today, look at the geometry of the physical world a little differently, keep questioning the tape measure, and as always, stay curious.